Alright, so continuing on chapter 11, ready for the Know Your Children worksheet. So the Know Your Children worksheet starts off with just some definitions, some things that we've looked at before, right? So the first thing here, the probability of an event, right, is a ratio, right? And this is the classical definition. So it's a ratio between the number of ways the event can occur, right? Number of ways event can occur compared to the total number of outcomes possible, right? Total number of outcomes possible, right? So that's what that's saying here. And then we're told the collection of all possible outcomes is called a sample space, and the event is considered to be a subset of the sample space, right? So some other things that are true is that the probability of some event is always in between 0 and 1, right? And it could be equal to 0 or 1. If the probability of the event is equal to 0, it means it will not occur, right? There's a 0 chance. Where if the probability of the event equals 1, this implies it will occur, right? Guaranteed, 100% certain, right? So let me give just a simple example. Let's say you're rolling a dice, right? Or I guess that would be just die, right? Let's say you roll one die, right? Let's say you want to find the probability of rolling a 5, right? So the sample space is equal to 1, 2, 3, 4, 5, 6, and the event here would be the set containing just 5, right? The number of ways it can occur is just 5. So being a subspace, for you guys, you can, or excuse me, a subset, right? Notice it says the event is considered to be a subset of the sample, right? So if this is the sample space for you, a subset is, you can think of it as like a smaller group, right? It could be the whole group or like a smaller group, right? So in other words, what things in here make this event true, right? So there's only one possibility of getting a 5, right? I'm only rolling one die, right? So the probability of 5 would be the number of ways to get a 5, which there's only one, divided by the total number of possibilities, right? So I have 6 possibilities, so 1/6, right? So probability of rolling a 5 is equal to 1/6, right? So that just trying to help make some sense of that notation, right? So a simple example, right? So we'll continue on with this, with these terms. So we're given this scenario: you meet with a friend who has 2 children. What is the probability your second child is a girl? Assume the probability of having a boy or girl is equally likely, right? So we're asked, what is the sample space for all possible ways she can have 2 children, right? So the sample space is all possible ways, right? So we could have a boy, we could have a boy first then a girl, we could have a girl first then a boy, and we could have 2 girls, right? So these are all the possible ways to have 2 children, right? There's just 4 ways. So then number 2 says list the outcomes for the event that we have a second girl child, right? So we just come up here and look, which ones have a girl second, right? Well, this one does and this one does, right? So that's the only outcomes is boy, girl, then girl, girl, right? So number 3 says now compute the probability that the second child is a girl, right? So this probability would be equal to, so there's 2 ways to get a second child girl, right? Those are the outcomes. So the number of outcomes that this can happen are 2. And then the sample space, how many are in here? We have 4 total, right? So 2 out of 4, or that reduces down to be 1/2, right? So the probability of having your second child be a girl is 1/2, right? Or we can show that as 50%, right? So then now we're told that she mentions one of her children is a boy. Given this new information, what is the probability that her second child is a girl, right? So if we look back up here at the sample space, so if we're told one's a boy, then this option can't be true, right? Two girls, because at least one has to be a boy. So in other words, it removes the girl possibility, right? So if we only have two children, at least one's a boy. We can't have both girls then, right? So my sample space becomes boy boy, boy girl, and girl boy, right? That's my new sample space now, given this information. So now we're computing the probability that the second child is a girl, right? Given this new information. So if you remember from up here, there are three ways that in my sample space now, right? So the number in the sample space goes on the bottom, and then how many of these have a girl second? Only this one, right? So this would be 1/3, right? So the probability now is 1/3, right? Knowing that. So this is 33.3% if you want to list it as a percent, right? Right, because there's only one outcome that gives me a second child being a girl, and there's three possibilities, right? So 1 out of 3, 1/3. So now it says, lastly, she tells us previously mentioned the boy was born on a Tuesday. Given this new information, what is the probability that the second child is a girl, right? So number 6 says, how does this information change the sample space, right? So there's actually a really good picture in the text. So let me open up the textbook for you. So I'm just going into Canvas, opening up my math lab. Then we're going to go to the textbook. So we're in chapter 11. I think this might be in 11 too, right? I'm pretty sure it's on page 11 in this section. So 11-11. Yep, right here. All right, so let me get a better full screen picture here, right? Actually, let me do this. So I'm going to take a screenshot of this and throw this into OneNote, so that way we can write on it. Right. So this is on the table 11.4 on page 1111. Right. So I would check out this. Check out that table, right? Because we're going to need this. So let me go over to the right here, and I'll blow this up for us. Right? So some things to notice. So along the rows, this is labeled as first child, right? So we could have a boy as our first child born on a Monday, a boy born on Tuesday, and so forth. It goes through all the days of the week, and then we go girl Monday, girl Tuesday, girl Wednesday, and so forth, right? All the way down, all the way to Sunday, right? So there are 14 rows here, right? So there are 14 rows here. And then there's also going to be 14 columns, right? But notice we have these dots, right? That means it keeps continuing on in that pattern, right? So we would actually list all of these at the top, right? The same row names would go along the top also, right? But the text chose to not list them all exactly, right? Skip over some. So what we need to do, so this is how it changes the sample space, right? This is my new sample space. So number 7, if you notice, says now compute the probability that the second is a girl, right? So to calculate the probability that the second is a girl, right, I need to look at, well, how many possible outcomes are there, right? So knowing that the boy was born on a Tuesday, right, this row is going to be all possible outcomes, right? And also this column is, right? So there's 14 along the row and 14 in the column, right? But one thing we have to be careful of is this guy gets counted twice, right? That's in the same row and the same column. So the number in the sample space is 28 minus 1, right? Because I, excuse me, I don't want to count this boy twice, right? Having a boy on Tuesday and another boy on Tuesday, right? We don't want to count him twice. So there's 27 things in my sample space, right? So the things in my sample space are what I highlighted in green, right? And again, not double counting this guy, right? Because there, if I skip over him, right, then there would be 13 in the column, right? Skipping over him, and that means there's 14 along the row, right? So 13 plus 14 is 27, right? So now I need to count the ways that has a girl being the second child, right? So the columns are the second child. So what would give me a girl being the second child would be this one: Monday, Tuesday, and then we would have Wednesday, Thursday, Friday, Saturday, and then lastly Sunday, right? So there's 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5, 6, 7, right? 7 ways, right? The girl could be born on any day of the week, right? So that would be 7 out of 27 ways. So this comes out to be approximately 25.9%, right? So whenever you're trying to find probability, right, the easiest way is we need to list the whole sample space. The number of things in the sample space goes in the bottom, right? And what goes in the numerator is the number of ways that your event can happen. And my event is having the second child be a girl, right? And all of these things aren't considered, right? All of these things aren't considered that aren't in green, right? Because that doesn't have my boy being born on a Tuesday, right? We know that's the case. So those aren't being considered, right? That's not a possible outcome, right? Because we know we have a boy born on Tuesday, right? All right, so we did 7 here, right, which is 25.9%, and my sample space is over here, right? That's how it will change, right? So now we're ready to look at the fundamental principle of counting, right? So what this says is, given a series of k choices to be made, where each one has a different option, right? So we have n1, n2, nk. These are the different options. Then the total number of possible ways to choose one option from each of k is the product. So we multiply, right? So this is the fundamental principle of counting, right? So let me do an example here. Let's say you are making up a PIN on your cell phone, right, to unlock it, right? So typically with the PIN, there are 4 options, right? 1, 2, 3, 4, right? We have to enter in 4 numbers, right? So for the first digit, right, I have 10 options, right? I can put in 0 through 9. For the second number, I have 10 options. I can put in 0 through 9, right? And the same with 3 and 4, right? So if I wanted to count what are the total number of ways, total number of pens that someone could have, right, if there's only 4 options, that would be equal to 10 times 10 times 10 times 10, or 10 to the 4th, right, which is 10,000. So there are 10,000 different ways to make a pen, right, if there's just 4 numbers and we're putting in one of the digits, right, and we can repeat the digits, right? So for example, we could have a pen of 1, 1, 1, 1, right? would be a possibility, right? So that's what this fundamental principle of counting is about, right? So here's another example, number 8. So here we have 2 shirts, 3 shorts, and 3 hats to choose from, right? So I think of it as I have like these 3 kind of bins, right? We have shirts, we have shorts, and we have hats. So we have 2 shorts to pick from, right? So there's 2 options for shorts, or shirts, right? There are 3 options for shorts, right? So that 3 would go here, and we have 3 hats. So I multiply these together, and so 2 times 3, we get what? 18, right? So there are 18 different outfits possible, right? So that would be that, right? So number 9 is drawing a tree diagram, and this just helps kind of illustrate why it makes sense for us to multiply, right? So a tree diagram is a visual way to look at this. So we have 2 possibilities for shirts, right? I have shirt 1 and shirt 2, right? 2 shirts. And then from each of these, I'm going to have 3 shorts, right? So short 1, short 2, and shorts 3, and then I would have shorts 1, shorts 2, and then shorts 3. And then off of each of these, I would have 3 hats, right? Hat 1, hat 2, hat 3, and then hat 1, hat 2, hat 3, right? Each of these would have this, right? So we'd have 3 hats here, 3 hats here, 3 hats here, right? And if we follow the diagram, so if I follow the diagram, shirt 1, shorts 3, and hat 2, right? If I follow that diagram, that's one possible outcome, right? One possible outfit. So all these things here would be the possible outfits, right? So you can notice I have 2 groups, right? Every time I have different options, it splits it in more groups, right? So this lends itself to multiplication, right? So I have like two groups of each for each shirt, right? And then depending on what shorts I pick, I have 3 groups, right? Of 3, right? So when we have equal groups, that's multiplication, right? We're just counting all those different ways. All right. So before we go on to permutation and combinations, I want to take a moment and look at a homework problem with you. So let me open this up. Let's see. So I have Pearson open here. So this is an 11.2 homework. Let me see what problem I wanted to look at. I want to look at this problem, right? So we have Simon, Maria, Tyrone, Sarah, Katrina, Larry, and Sergio, right, have all been invited to a dinner party. They arrive randomly, and each person arrives at a different time, right? So I have 1, 2, 3, 4, 5, 6, 7 people, right? So let me write that down. I have 7 people, right? 1, 2, 3, 4, 5, 6, 7, right? 7. So part A says how many different ways can they arrive, right? So I have 7 options, right? Someone can arrive first, someone can arrive second, third. Let me actually make this a little wider. Right? So someone can arrive third, someone can arrive 4th, 5th, 6th, and 7th, right? So these are all the different places. So think about this. How many people can arrive first? Well, there are 7 different options for first place, right? One of the 7 can arrive. If we think about how many people can arrive second, well, that's going to end up being 6, right? Because if one person already arrived first, then that leaves one less person to arrive second, right? Similarly with third, right? So if 2 people are already at the party, there's only 5 people left that can arrive third place. And then if you keep following this logic, we would keep subtracting 1 each time, right? So we get 7, 6, 5, 4, 3, 2, 1, right? And using the fundamental principle of counting, right, to figure out the number of ways, we would want to multiply all these together, right? So 7 times 6 times 5 times 4 times 3 times 2 times 1, right? This is known as a factorial, right? 7 factorial is equal to 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So if you think about this for a moment, like for example, if we had, I don't know, 24 factorial, right? This would be equal to 24 times 23 times 22 times 21 times 20 times 19 times ... all the way until you got to 1, right? So when you take a factorial of something, you start at that number, and then you keep subtracting 1 each time until you get to 1, and you multiply all those things together, right? So that's known as a factorial in mathematics, right? So and there's an easy way to do this in your calculator, right? So you know, depending on what version you have, it's similar, right? We need to go to 7, and typically this is found under the probability menu. So we're looking for PRB, which on my calculator is under math, and then there's a PRB list under here, right? So PRB, and then the option 4 is my factorial, right? So if I hit enter, there's 7 factorial. So 7 factorial is equal to 5,040, right? So that is my answer for part A, right? There's 5,040 different ways that these people can arrive. So then in part B, right, so we can go ahead and type this in, right? So in part B it says, in how many ways can Simon arrive first and Sergio arrive last, right? So again, I have 7 places, right? Right? So if we know that Simon is first, there's only one option for first place, right? That is Simon. If Sergio is last, that leaves only one person left for 7th place, right? Last place, because those are fixed, right? So there's one option here, one option here. So then for 2nd place, there are 5 people left over, right? Because 2 were already taken out because we put 1 at first and 1 at last. So then there would be 4 people left for 3rd place, 3 people left for 4th place, 2 people left for 5th place, and 1 person left for 6th place, right? So using the fundamental principle of counting, we multiply all these together, which that's the same thing as 5 factorial, right? 5 times 4 times 3 times 2 times 1, right? So 5 factorial would be the number of ways that Simon can arrive first and Sergio can arrive last, right? So we can type that in our calculator if we'd like, right? So we need to make this 5 factorial, hit enter, we get 120, right? So this is equal to 120. So we type in 120 here, and then now we're asked, find the probability that Simon will arrive first and Sergio will arrive last. Right, so there's a couple of ways that we can do this. So part C, finding the probability that that we have Simon first and Sergio last. Right? So the total number of outcomes that we found was part A, right? Part A would be my numerator, which is 7 factorial, right? So this is 7 factorial. And then the number of ways that event E can happen is what I found in part B, right? So that's 5 factorial. So I can simplify these, right? So simplifying factorials isn't too bad, right? So 5 factorial I can leave in the numerator, and 7 factorial is equal to 7 times 6 times 5 factorial, right? Because 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And this portion is simply 5 factorial, right? 5 all the way down. So the reason why I chose to write it in this fashion is because now 5 factorial divided by 5 factorial is 1, right? So those cancel out, just like reducing down a fraction. So I end up with 1 in the numerator and 7 times 6 in the denominator. So 1 over 42, right, is my simplified version, right? So you can do it that way by simplifying radicals, or you could, use your calculator and take 120 divided by 5040, and we can turn this answer into a fraction, and we get 1 out of 42, right, which is what I got using the factorials. So we can do that either way, right? Doesn't make a difference, however you want to do that, right? All right, so that'll give you some more practice with that fundamental principle of counting. All right, so let me close out of this. Go back to worksheets. Right. So now I'm ready to look at permutation and combination. Right. So the big things that you want to remember off of these notes is that a permutation is when order matters, right? So with a permutation, order matters, right? With a combination, order doesn't matter. Right? And then also we need to remember this equation, right? So some ways to denote this, we have P and then we have N and R here, and this is equal to N factorial all divided by N minus R factorial, right? And then a combination is NCR, right, denoted equals N factorial divided by N minus R factorial times R factorial, right? So these are the equations, and you should definitely know these equations, right? So an example of a permutation that we're going to look at is like number 11. So we want to consider, well, if we know we have 12 people in a class, how many different ways can we choose a committee of 4? Right? So number 11 is a classic example for a combination. Right? So order doesn't matter here because we're putting people on a committee, right? So if you chose first for a committee or third for a committee, it doesn't make a difference, right? You're just on the committee. You're a committee member, right? Makes no difference. Where number 10, here it said given 12 people in a race, how many ways can they finish first and second? So order does matter here, right? So if Tom came in and then, I don't know, Bill, right? This is not the same thing as Bill, comma, Tom, right? Because this has Tom being first place, and over here Tom is in second place, right? So those aren't equal. So order matters in this case. So we use a permutation, right? So if you have trouble remembering which one's which, the way I remember is it's the opposite of what you would think if you think about a combination lock, right? Because if you have a combination lock, if your combination is 1, 2, 10, right? The only way to open that lock is putting them in the right order, 1, 2, 10, right? If you change the order in a combination lock, you won't be able to open the lock, right? So it's the opposite of how a combination lock works. So in a combination lock, order matters, but in a mathematical combination, order doesn't matter, right? So I always joke that a combination lock should be called a permutation lock, right? So we need to change the name of the lock, right? So that should help you or could be a helpful tool to help you remember the difference between the two, right? Help keep it straight. Right? So as I was saying, number 10, I pointed out that a permutation is appropriate here. Right? So to be able to do this, we just need to use this formula, right? So so n is the total number of people in the group, right? So there are 12 people in the group, and then r is how many things that we're selecting, how many items we're selecting. So we're selecting just 2 items, right? Because we have a first and second place. So the notation we would do is 12 P2, right? And this is equal to, so just following our equation from above, right? We have n factorial, so we'd have 12 factorial, all divided by 12 minus 2 factorial, right? So this is n factorial, all divided by n minus r factorial. So this is equal to 12 factorial divided by 10 factorial, right? But remember from before, we can reduce this, right? 12 factorial is 12 times 11 times 10 factorial. And then on the bottom, I have 10 factorial. So these reduce out, right? They can divide out. So we're left with simply 12 times 11, right? Which is, 132, right? So there's 132 ways that 12 people can finish a race in first and second, right? So to verify this, you can also do this in your calculator. So to do this, you first enter in the n value, which is 12, and then you have to go to that probability menu, and you want to look for NPR, right? Because we want to do the permutation. So I click that. So this side goes in, I hit this button, and then now I'm going to put in R, which is 2. And then if I hit enter, it'll generate that for me, right? I get 132, right? And I can also think this simply using the fundamental principle of counting, right? So if I have 2 options, right, first place and second place, then there are 12 people that can finish in first place, right? So, and then in second place there would be 1 less, right, because 1 person finished in first. So this would be 12 times 11, which is also 132, right? So we can think about this in terms of permutation, or this example could also follow using the fundamental principle of counting, right? All right, so the number 11, we're going to use a combination, right? So n is 12 here, r is 4, right? We're choosing 4 items. So the notation would be 12c4, right? So this is equal to n factorial, so 12 factorial, all divided by n minus r, so 12 minus 4 factorial, and then times r factorial, which is 4, so 4 factorial, right? So we can simplify this. I would have 12 factorial on the top. 12 minus 4 is 8 factorial times 4 factorial. So 12 factorial is 12 times 11 times 10 times 9 times 8 factorial. And then I have 8 factorial on the bottom times 4 factorial. So these 8 factorials will reduce out, right? I can divide top and bottom by 8 factorial. So then what I have left is 12 times 11 times 10 times 9 in the numerator. And then I have 4 factorial in the denominator. So that's 4 times 3 times 2, and then times 1, right? But really I don't need the times 1, right? It doesn't make a difference. Anything times 1 is just itself, right? So we could pull that out. So then something you could note is that 4 times 3, right? This 4 times 3, this is simply 12, right? So these guys will cancel out with the 12, right? 12 divided by 12 is 1. So those cancel out. And then let me rewrite that 2. Right? So then we had times 2 here. So now one thing I could notice is 10 is the same thing as 5 times 2, right? So instead of writing 10, I could replace it with 5 times 2. So then you can see easily that my 2's would cancel out, right? So then what I'm left with is 11 times 5 times 9, right? All over 1. So 11 times 5 times 9. right? So 11 times 5 times 9 gives me 495, right? So this would be 495. So and if you wanted to double check this in the calculator, right, we would need to enter in 12, and then go to your probability menu. We want to do the NCR because we're doing combination, and then I need to type in R, which is 4, hit enter, and we get 495 that way also, right? So if on like if if a question like this was on the final exam, I would expect you to be able to use the equation, right? So you can put this on your formula sheet for the exam. You can use your calculator to check, but I would expect you to be able to calculate, right? Not just write down an answer, not just write down a number. I want to see your thinking involved, right? So be able to do the equation, but you can certainly use that function in your calculator to double check and make sure you're on the right track, right? All right, so then the next thing that we need to work on is what we call conditional probability. So conditional probability is finding the probability of some event given something is already true, right? So here we have the conditional probability of A given B is written probability of A and then a line B, right? So this is the ratio of number of outcomes occurring in both events A and B to the number of total outcomes in B, right? So number 12 is an example where I'm trying to compute the probability. So we're calculating the probability that we have, the probability of having a smoker given that we have a male, right? So this is our condition, right? So what's the probability of a smoker given given I have the condition that we have a male, right? So if we look at, so I don't care about females, right? Because I'm already told we're given a male. So I'm only worried about this column, right, of males. So how many males total do I have, right? Well, I have 380, right? So that's my total number in the sample space, my total number of outcomes, right? And then we look at, well, how many are satisfy the event, right? In other words, how many of them are smokers? Well, there's 130 that are smokers, right? So the probability of having a smoker given that we have a male would be 130 out of 380, right? I have 380 males and 130 of them are smokers. So if you wanted, we could get a percentage. So we take 130 divided by 380, multiply by 100%, we get roughly 34.2%, right? So this is roughly 34.2%, right? So then lastly, we're asked to calculate what's the probability of a female given that we have a non-smoker, right? So I'll do this in blue, right? So we're given that we have a non-smoker, so I'm only worried about this row, right? This in blue. So I have 465 non-smokers. So that would be here, right? So I'm only considering this group of non-smokers. And then what's my probability if I pick a random person out of here, of the non-smokers, what's the probability that they would be a female, right? Well, there are 215 people in this group that are female, so this would be 215 out of 465, right? And we can divide those to get a percentage, right? So 215 divided by 465 multiplied by 100%, we get 46.2, right? So this is roughly 46.2%, right? So this table is often referred to as a two-way table, right? So you want to be able to find conditional probability is given a two-way table, right? All right, so that's the end of this worksheet. Let me know if you have questions.